Greetings, physics fans. Let's do a lecture on our optics. And what I'm going to try and do in this lecture is cover all the principles between our mirrors and lenses and just get all the tricks that we're going to see. So let's just do our quick summary of what you're going to encounter, okay? And I'll start with our primary optical instruments. All right. So this is going to break down to four things. We're going to have a concave mirror, so here's the setup. Here's my mirror. It caves inwards. This is going to be my optical axis. Optical axis. And we're going to be shooting rays in like such at this mirror. And points that we're going to have to specify. There's the vertex, which intersects the optical axis. We have one point way out here. Often labeled a capital R, and that's called the radius of curvature. Basically, think of the mirror as being this spherical ball, and you're looking at just a slice of this curved mirror. And then we'll have the focal length, F. Right? So one thing that's always going to be true is that the radius of curvature is 2 times the focal length. Now, if you've been going ahead looking at your problems, you might see some focus on F, some focus on R. Why the distinction? Well, R is a geometric thing. R came from the geometry of the mirror. F, the focus, that comes from an optical property. And a little bit we'll actually go through why we care about F way more than the radius of curvature. So that's our concave mirror. Let's do our next one. It'll be a convex mirror. How do I know if it's concave or convex? Well, let's draw the shape of the convex mirror. Pretty similar. It's going to be once again optical axis. Move here a little bit. Same thing. There's a vertex. And we can have the radius of curvature of this mirror. It similarly has a focal length. Same thing. The radius relationship is just double the focal length. And once again, we'll be shooting rays in like so and seeing how they reflect off of this mirror. So our relationship is concave. The rays, or the curvature of the mirror, is caving in. Convex, going outwards. Right? So that's our 2 main mirrors that we're going to discuss for this class. And we also have 2 types of lenses. So we can have let's make that. We have our converging lenses. They're going to look like kind of like a teardrop almost. And one thing we'll notice is that our lenses are going to have 2 focal points. Mirrors have 1, lenses 2. So from here to here, that's a focal length. Here to here, that's a focal length. And always, we're going to be sending rays, and I'm not going to draw it this time. Right. Converging, the curvature lens is outwards. We also have a diverging lens. This one looks like we've hollowed out a little bit. Our diverging lens cave inwards. same thing, 2 focal lengths, but things to emphasize here. Here, for the converging lens, that focal length is a positive number. Must be a positive number. We'll get into details why in a little bit. For the diverging lens, that focal length is a negative number. Right. I'll wait until I start showing rays going through these to explain why it is that way. Come back to these guys. Well, they have focal lengths too, the mirrors. Well, my concave mirror has a positive focal length, whereas my convex mirror, negative focal length. All right. The sign conventions, it's going to be about where the rays are coming in versus where the image is forming. Right? And you can hear me say this a couple of times. Honestly, it takes just practice. You need to practice getting these sign conventions right. So, some equations that we're going to need, and that's really going to be about the extent of formula we need. We're going to have our image-object focal length relationship. And yes, there's a couple of different ways to write this. I'm going with this way. I can say 1 over what's called the object distance plus 1 over the image distance equals 1 over the focal length. All right? And this applies, make that legible. This applies to every lens and mirror shown here. Every single one of these. Similarly, we can have the magnification, right? Definition, it's the ratio of the image height over the object height. Or it turns out that through some tricks in geometry, we can relate this to minus the image distance over S. All right. So make note. We must be careful with our signs. Our signs are really going to dictate what mathematically we're going to produce. And if you struggle with signs, we also have what are called principal rays. Right? So we can solve problems using the equations. And using what's called the principal rays. All right. Principal rays are going to be our powerful tools, and if you're listening to this now, know the principal rays. I'm going to use these constantly and expect you to know them too, because these are a great tool because all you gotta do is draw lines, draw straight lines. If you can draw the rays, the mathematics is trivial. You can use the pictures to check your work, to check your algebra. So I'm going to emphasize here that we use our principal rays. We draw principal rays to find where images are going to form through our lenses and use the mathematics to just confirm our observations. So let's start setting these up. Let's set up what our principal rays are. There we go. We'll start with the mirrors. All right. 1, 2, 3, 4. There's going to be 4 of these principal rays that I'll discuss here. Right? Rays that are parallel to the optical axis those get reflected through the focal point. All right. What do I mean here? All right. Here's my mirror. Here's the optical axis. All right. And now I'm just going to shoot an array, and I'll actually make them nice and straight. All right. So I've got this ray coming in. Where does it reflect through? All right. So it's going to hit a mirror, and then it has to bounce off. Well, I say identify the focus. This mirror has a focus there. Well, then send the ray just straight through the focus. And so that ray reflects like that. Right? Similarly for the convex mirror. Right? Here's our convex mirror. Here's our optical axis. Put the focal length there. And let's just send a ray in. We'll send a ray coming in parallel to the optical axis. It comes in parallel. Oops, that focus is in the wrong spot. Focus is behind the mirror. Did I draw that right first time? Yes, I did. All right, good. All right. The focus is behind the mirror, and say, all right, well, it has to be reflected through that. Well, since this is a mirror, it can't pass through the mirror. It's got to reflect. So what we say is, look, let's draw a little dashed line here. There's a projection, right? Dash means projection, and this is going to tie into what we mean when we say a real or virtual images. There's this projection here, and the reflected ray actually goes off like so. All right. So that's our first principal ray. Parallel the optical axis through the focal point. For the convex mirror, the ray is literally passing through the focal point. Concave. For the concave mirror, goes through the focal point. For the convex, the image will go away. Right? The ray you project back to the focal length, and then figure out where the ray is going. So let's go on to our next one. Our next principal ray. Rays that pass through the focal length, or through the focal point. Well, those get reflected parallel to the optical axis. It's literally the inverse. So we'll just draw these again. Here's my optical axis. And we'll do this guy at the same time. There's my focal. There's my focal. All right, let's bring in my handy mirror. So let's have a ray that comes in like this. It's coming and it intersects the focal point. Boom. It hits that focal point. Well, then it must reflect parallel to the optical axis. So here it is leaving the system. All right. What does it mean to be aimed at the focal length for the convex mirror? Let's do a ray like so. It's aimed at the focal length. Remember, ray comes in. It's aimed at the focus. It can't get there. It can't pass through the mirror. But we can always do the projection. Dashed lines, projections. Right. So here's my ray coming in. It's aimed at the focal length. It's aimed at that focus. Well, then the reflected must come out nice and parallel. And there's my outgoing reflected ray. All right. 2 more to go for the mirrors. All right. Rays that pass through the radius of curvature. If it passes through the radius of curvature, then it's going to bounce and come right back through that point. Here's my mirror. Here's my second mirror. Optical axis. You need to get into the habit of drawing these. Seriously, guys, if you have not been paying attention to me this whole semester and not drawing, you've only screwed yourselves now. There is a reason why I constantly say, draw a picture. Because it's a powerful tool. Here, we're literally using the pictures to solve all these problems. Like, the math is trivial simple. All right, so my rant's over. Let's go back to black for a second. So let's say this was the focal length. Oh my gosh, gotta turn off the ruler. So there's my focal. Here's my radius. Focal. Radius. All right. Now let's start shooting some rays in. I said if it passes through the focus, then it has to bounce back the same direction. So this ray comes in, bam. Ray comes in. Well, then the outgoing ray, I'm going to use a color, all right? I'm going to color code it. Then the outgoing, the reflected ray, is doing the exact same thing. Not to imply there's a color change, right? Let's do the same thing with this guy. Let's come in. Let's do a nice shallow angle. So it's aimed at the radius. There's that projection again. Well, it hits the mirror. It's aimed at the radius curvature, and it just comes right back. All right. Last one. Last principal ray for our mirrors. All right. Rays that hit the vertex now. If you hit the vertex, then you get reflected at an equal angle. It's like hitting a flat mirror if you hit right at the vertex. All right. Last batch of mirrors. So now there's our vertex right there. So let's come in at a nice 30 degrees. So this ray, bam, it hits the vertex, and then it has to reflect at the exact same angle. So it comes in, and then it leaves. All right, and pretty much looks exactly the same for the other mirror. Let's do a different angle. Let's do something extreme. Let's do like 60 degrees. I'll do 50. Ray comes in, bam. It hits at the vertex, so the reflected bam. Incident. Reflected. All right. So there's our 4 principal rays. Right. In fact, you need a minimum of 2 of them. You need at least 2 of these rays to define where the image forms. All right, so let's do some practice with this, right? We'll do lenses after we've done our mirrors, right? So here's our setup. Let's have one mirror. Let's do a concave mirror. F is going to be 10 centimeters. S, that's that object distance. S is going to be 30 centimeters. I want you to find where the image is and the magnification. All right. So first, draw it out. I'll do it this way. First step, draw principal rays. Second step, then do the math. If you do the math before you draw the pictures, no, cut that out. Draw your principal rays first so that when you have a bunch of math, which is just numbers that don't have any meaning, you can compare them to the pictures that give the numbers meaning. Have I made myself clear that we always do our pictures first? Always. All right. So I said a concave mirror, so here's my mirror. There it is caving in, and let's draw our optical axis. I said it's got a focal length of 10 centimeters. Let's say that's F. Let's go a little bit further out. Let's say that's F. And I said the object is 30 centimeters away, so I need to be further away from the mirror than the focus length. So here's going to be my object, and I'll make it just an arrow like this. So there's S, there's F. Now, find the image. Well, we're going to shoot in principal rays. My favorite, I always start with the one that's parallel to the optical axis. I always start there. So, Come on. Slow down. There we go. Really back. All right. So I'm always going to start off by shooting a ray that's parallel to the optical axis. Send that ray in and say, all right, you reflect through the focus. And there's one principal ray. Let's switch up colors. I'll shoot another principal ray. All right. One that I like. Let's go through. Let's see here. If I hit the. Let's go for the vertex. If I hit the vertex, by my drawing, it's about 16 degrees. Bam, hits the vertex. Now flip. Boom. So, where rays intersect is where the image forms. Right? Well, they intersect. I'll use orange here. Right there. That's where they cross. So here's S prime. There's our image. So things that we can expect, right? We expect this is a real image. Let's see, expectations from drawing. One is that this is going to be a real image. Why do I say real? Well, look at the rays. The reflected rays actually cross each other. They physically cross. And that's what we mean by real. There are physical rays crossing there. Also, we expect the image is inverted. That's to say that y prime should be a negative number. And finally, let's see here, real image. That implies that S prime is a positive number. Finally, we can say that the magnification, I expect it to be M is less than 1. These are the three conclusions we've got from just drawing two rays. Real image, inverted, magnification has shrunk. The arrow is a smaller arrow. Well, let's do some math. 1 over S plus 1 over S prime equals 1 over F. Some of you might recognize that this looks like some similar formulas to like when we did resistors in parallel or capacitors in series. All right. It is a very similar formula. They come from different physical principles. The similarities just come from the geometry of how these things are combining. All right. So we have S or F. Solve for S prime. I'll do it explicitly once. Right? 1 over S prime equals 1 over F minus 1 over S. 1 over S prime. Get them to have a common denominator. 1 over S. Multiply by S over S. 1 over S. Multiply by F over F. S divided by S is 1. F divided by F is 1. I'm taking the two terms here and multiplying by 1. So now they have a common denominator, and we can just combine. This is now S minus F over S times F. Invert. S prime is now equal to S times F over the difference, S minus F. If you must, you can write this down as an equation to remember. I don't, because all I need is that, and I apply some algebra skills. But some students say they like memorizing this. So be it. Whatever floats your boat. Let's plug in our values in. Right. S prime is equal to, let's see here, 30 centimeters, 10 centimeters, everything's positive. 30 centimeters minus 10 centimeters. Or that's to say 300 divided by 20 centimeters. Or 30 divided by 2. Or S prime is equal to a positive 15 centimeters. Bam. And look, that confirms with what we said here. We said that the image must be positive because it's a real image, and our math agrees, say it with me, with our drawing. All right. So now let's get that magnification. All right. Definition. Magnification is y prime over y. Don't bother solving for the image height. I didn't ask for it. So instead, just go to m is minus s prime over s. In fact, we'd have to use this equation to get y prime. All right. We'll just plug in our values. This is minus positive 15 centimeters over, come on, over 30 centimeters, which gets you minus 1/2. All right. Let's try another problem. Same mirror. All right. We'll have our same convex mirror. F is 10 centimeters. And we're going to move where the object is. We're going to say S is 5 centimeters. Find S prime and M again. Start with the drawing. All right. I'm going to zoom in a little bit. So here's F. Here's S now. And I'll put the object here like so. Now let's start bringing in our rays. All right. Rays I'll use. I only need to use 2. We have 4 in total. I'll go with shooting through the vertex again. I liked that one a lot. So I'll shoot through the vertex again. And at this figure, it looks like it is 31 degrees. So the ray comes in at 31 degrees, hits the vertex, reflects at 31 degrees. Now I'm starting to hear the questions forming in your heads. No, you don't need to use a protractor. You can roughly estimate these angles. They'll get you close enough. The idea is just have the image form. It does not have to be this perfect scientific measured angles. I'm just using the tool because it helps me draw straight lines. Would recommend a straight edge. That's useful, right? So there's my reflected ray. Now I want to send another ray. I could go parallel the optical axis again. Let's go with that. And I'll use a color to distinguish these two. 1 second. Come on. There we go. So shoot in that ray. And then bounce it to the focal length. Turns out it's going to be about 19 degrees for this problem. So there's our rays going off to oblivion. All right, notice something. So the reflected rays don't converge. They're going off at different angles. They'll never cross. So we can say that there is no real image. The rays never cross. So what do? Create a virtual image. By tracing the reflected rays behind the mirror. You trace back. You go back behind the mirror and see if they cross there. So let's bring our ruler back. And we start looking behind. And I'll use dashed lines because there are no physical rays there. We're just seeing the projections behind them. Now let's line up with you. Yes, we said 31 degrees. There's our dashed lines. And would you fancy that? There's a crisscrossing right here. Now there's S prime. So what we've learned, right? We've learned virtual image, which means that S prime must be a negative number. The image is behind the mirror. There are no physical rays behind the mirror. You want an example of this? Go to your bathroom right now and look at the mirror. Where do you see yourself in the mirror? You see yourself standing behind the mirror. There's no rays behind the mirror. There's a freaking brick wall or something like that there. But where your eyes focus the image is virtual. It's back behind the mirror. That's what I mean by virtual image. There are no rays physically there, but our eyes interpret the image as being that distance behind the mirror. What else have we learned? Let's see here. We've learned that the image is upright, and its magnification is greater than 1. This image should be bigger. Now do the math. We've done our picture, we've got our analysis, let's do the math. S prime is going to equal, I'll just jump, we'll use the formula we found before. S minus F, 5 centimeters, 10 centimeters, all over 5 centimeters, minus 10. So what do we get? 50 divided by minus 5. Yep, there we go. Which equals minus 10 centimeters. Would you look at that? Our math agrees with our image. This is the power of these utilities. We draw a picture, we figure out what we expect the math to be, and when we do the math, it agrees. This is why we do physics. All right, magnification. Magnification, once again, minus S prime over S. So minus, because it's a virtual image, all over 5 centimeters, which will be overall a positive 2. This image is twice as tall as the object. Would you agree that the image is about twice as tall as the object? All right. Let's do one more example of this. Same year. Oops. I wrote ref x when I meant concave. Sorry about that. Did I do the same thing up here? Yeah. All right. So concave, concave. Same thing. Using the same mirror. Concave mirror. Same focal length. S is going to be 10 centimeters. Find the object and magnification. All right. Do the drawing before the math. Cannot emphasize this enough, guys. So here's my focal. I'm just going to draw the object right on top of it. Well, let's start shooting some rays. Well, one ray I'll use the one that goes parallel the optical axis. Let's go parallel the optical axis. Bam. And that has to reflect through the focal. It's going to be about 30 degrees with this drawing. Now let's try. Let's do vertex again. All right. Always just find a principal ray that you're comfortable with. So the vertex is going to be about 30 degrees. And so if it hits the vertex, it reflects at the same angle as the incident angle. So here's a nice 30 degrees. Boom. All right. Look at this. Same conclusion as before. Okay. Reflected rays never cross. So do the projections. Try and find the virtual image. So we look behind the mirror. And some of you might notice the issue. This ray, it's at a 30-degree angle. This ray is also at a 30-degree angle. So the projections also never cross. What the heck does that mean? Well, all we have to say is no image is formed. There just is no image when you're standing right on top of the focus. Let's do the math. Do the math to check ourselves. All right. S prime is S times F over S minus F. So we said 10 centimeters, 10 centimeters, 10 centimeters, minus 10 centimeters. Warning sign. What's 10 minus 10? 0. What's 1 divided by 0? Undefined. Things explode here. So all we say is that S prime approaches infinity. We say it blows up. And that, in this case, there is no image. Alrighty. Let's go on to our lenses examples now. let's do our principal rays for lenses. All right, first one should be familiar. If the ray is parallel to the optical axis, well, then it refracts. Mirrors reflect, lenses refract. If you're parallel to the optical axis, then refract through the second focal point. So here's my converging. There's my diverging. Focus, 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 focus. So I shoot a ray in. If I shoot a ray in here, bam. The second focus for our converging lens is this guy. Boom. So that ray converges through the focus. For our diverging lens, we come in. What's the second focus? Well, it's actually the one that we've crossed over. The minus sign is what's flipping up the language of what's the second focus. Diverging lenses have negative focal lengths. So we have to go like this. We go through that focus and diverge away. Our next principal ray. If your ray goes through the center, then there's no refraction. If you hit the center of the lens, some resources you'll see them do a little dash line there to help with the drawing. All right, the dots mean the center of the lens. And if you're wondering if you actually read your textbooks, why they use thin lenses, the word thin lenses, this is why. So if you go through the center, bam, well then you just get to keep passing through. Same with this guy. You hit the center, and you keep moving. All right. Last one for our lenses. So a ray through the first focal length. And it's basically the inverse of the first principal ray. focus, 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 focus. So, if I go through this focus, bam, I'll say not everyone does the dots. I get lazy. I sometimes draw them. I sometimes don't. All right. Cross through the first focus. Oop. You come out nice and parallel to the end. What about this guy for the diverging lens? Well, that means that you are aimed like that. Let's go nice and extreme. Right? Because the first focus is along the opposite side of the lens for the diverging. So you're aimed there, which means you come in at this angle, and then you refract out and a nice straight line. So there's our principal rays for converging, diverging lenses. So before we do the problems, what are they called? Converging and diverging. Well, let's do a converging one first. Make this nice and big. So let's shoot in nice parallel rays. Let's say we've got a nice bright laser source here. So we shoot in our rays nice and parallel. All right, parallel rays come in. How do they go out? Well, let's do the easy one. If you cross through the center, you just get to keep going. If you're parallel to the optical axis, well, then you reflect through the focus. And this one, parallel to the optical axis. So you gotta hit that focus. What in the world? Come on, undo. Yeah, I don't want that one. Why is that there? There we go. That was weird. Let's do this again. Right. So we'd say, bam. Rays are focused. They converged at the focal points. If anyone was ever weird as a kid and played the magnifying glass to set leaves or ants on fire, if you were sadistic, you were playing with a converging lens. Now, what do you imagine you'll find when you use the diverging lens? I'll try and go through this one a little bit quicker. So once again, shoot in our rays, nice and parallel incident rays. One above, one on the optical axis, and one beneath. Shoot in nice parallel rays. Now let's get our focal points here. So what do? You refract with respect to the second focus, which for diverging lens is the opposites. So this guy flies off like that. This guy flies off like that. And this guy, well, it went straight through the center. So you get to keep going. The rays diverge. They fly away. All right, let's do some practice problems using the diverging lens. All right, so we got diverging lens, which means that it'll have a focus length of minus 10 centimeters. And we're going to do the same thing. S is 30, S is 5, S is 10, all right? S equals 30 centimeters. Find S prime. End it. Say it with me. Draw the picture first. We got ourselves a diverging lens. Here's our focus lengths, and we'll have our object over here. There's our object. So let's shoot in our rays. I always like to do the one parallel the optical axis. Me personally, I find that one to be the easiest one to start with. It's a diverging lens. So we got to blow up, blow away. So you say, look, fly off in that direction. Now let's do another one. Well, let's change colors. Let's do the one aimed at the far focal length. So we're going to do this guy. Ray comes in. If you are aimed at that, then you better come out nice and straight. All right. Is it a real or virtual image? Well, the rays don't cross, so we must get a virtual image. Well, we've already traced one of them back. Let's trace the other back. Let's zoom in on this. Gotta trace this guy back. And we see where they cross. There's our image. It's a virtual image because the real rays do not cross. So we have to say S prime, it better be negative. The magnification, magnitude-wise, right? Magnification is a number that's less than 1 and upright. So, do our math. S prime. I'm just going to power through this quickly. All right? It's going to be SF over S minus F. S. 30 centimeters. Diverging lens. Minus 10 centimeters. 30 centimeters minus 10. So I get minus 300. Let's see here. There we go. Minus becomes positive. So it becomes positive 4. Or overall minus 3/4 centimeters. Nope, 30 over. Too many powers 10. Right, minus 34th, or S prime is minus 7.5 centimeters. Look at what the math just told us. This is amazing. Minus sign. Minus sign. We got a virtual image. Our diagram agreed with that. Minus 7.5. Well, if the focus is 10 centimeters, if this distance is 10 centimeters, our virtual image better be a distance less than 10 away. And our math says it's less than 10 away. So our math is agreeing with our pictures. Our physics is consistent. All right, you know the drill. Now F is minus 10. S, we're going to make 5. Find S prime. Oop, skipped M the first time. M is minus 7.5 over 30, which turns out to be positive 1/4. Let's give myself a little bit more space here. Let's do this. So F, object. And let's start shooting some rays in. All right, let's go parallel the optical axis. Parallel. You then diverge away because it's a diverging lens. Now let's do another one. And I'm going to go through the vertex. Just because the spacing here is tight. So we're going to go through the vertex. If you hit the vertex, no deviation. You just get to keep going. All right, say it with me. The rays don't cross. Real rays don't cross. Rays don't cross. So, must be a virtual image. S prime is negative. Well, where do they cross? Well, luckily, the way we've drawn this, we already got their crisscross. Let's zoom in. It's right here. So there's S prime. Therefore, we expect that S prime is a number less than 0, better be less than the focal length, and that M is still less than 1. Standing upright, but a shrunk down image again. Quick maths. S is 5 centimeters minus 10 centimeters, 5 centimeters minus 10. So minus 50 over minus 10, positive 15, which gets you minus 3.33, repeating, of course, centimeters. Whereas in that application, let's see here, hold on. It's minus, gotta be going too fast, minus 0.66, repeating. All right, last one. We'll have the object sit right on top of the focus. So F is minus 10 centimeters. S is going to be 10 centimeters. So there's my diverging lens. F. And there's my object. All right. Shoot in our rays. Rays. Oop. Come on. Let's get rid of you. All right. Yes, I want red rays. All right. Shoot in. Diverge. And then this time I'll do aim at the far guy. Aim at far. Come on. Slowing down on me. We don't have red dots anymore. We need them to be blue. There we go. So we aim there. And then refract, parallel the optical axis. All right, once again, rays don't converge, so project backwards. Let's project backwards. Would you look at that? Even in this case, we still get a virtual image. Virtual image, they do cross. S prime will be negative. N is still some number less than 1. All right. So we'll call it into the lesson there. I hope you've all learned a lot from this, and I'll see you all next time.